Okay, good. So now, in this section, we want to talk about the tangent and inverse tangent functions. Now, technically, there are three others, right? There's cotangent, secant, and cosecant, and those come up every now and then, but really the tangent, sine, and cosine are the ones that occur the most prevalently. And so I'm only going to focus on those. I'm not going to make you responsible for the other three. It wouldn't hurt just to Google them to kind of just see what they look like if you're unfamiliar, just in case you bump into them later on. But for all intents and purposes, the tangent, sine, and cosine are sufficient. Okay, so let's actually use the information about the sine and cosine value or functions to try to get an idea of what tangent looks like. So the very first question that we answer is, what's the domain, right? So remember, the definition of tangent is a quotient function. It's sine of x over the cosine of x. And so we know that the domain is the set of all numbers for which the bottom is not zero, namely the cosine isn't zero. Excuse me. But remember, the cosine of x is zero for inputs for which on the points on the unit circle are on the y-axis. And that occurs at pi over 2, 3 pi over 2, so on and so forth in both directions. And so the domain is the set of all x values that's not equal to one of those guys. And moreover, since this is a quotient function, at every one of the values that you're throwing out of the domain, you're going to have a vertical asymptote. All right, so a lot more exotic than the graph of sine and cosine were. In terms of symmetry, remember, we know that the sine function is odd and the cosine function is even. And so if we use those, let's compute tangent of minus x. That's by definition the sine of negative x over the cosine of negative x. But we know from our even odd identities that the top is equal to negative sine of x and the bottom is equal to cosine of x. But remember, sine of x over cosine of x is tangent. So we have tangent times a negative 1. What that tells you is that the tangent is an odd function. So its graph is symmetric about the origin, right? So the part to the right of the origin, you reflect over the y-axis and then over the x-axis. All right, so let's actually take a look at what happens on 0 to pi over 2, and then whatever it is, we'll reflect it over the x and then the y. All right, so first off, tangent of 0 is equal to 0, right? Because remember, tangent is sine over cosine. Sine is 0 and the cosine of 0 is 1. So we know that there's an x-intercept at 0, which is right between negative pi over 2 and pi over 2, right? This is the first period, so to speak, of the tangent graph, and it occurs at its midpoint. If you look at x values to the right of 0, so between 0 and pi over 2, those are angles in the first quadrant, and so the sine and the cosine are both positive there. And furthermore, as the x value goes from 0 to pi over 2, the sine, the top goes from 0 to 1, but the bottom goes from 1 to 0, which means it's getting larger. And so we know there's an asymptote at pi over 2. Everything is positive, so it starts at 0, and it follows that asymptote up to plus infinity as you approach pi over 2 from the left-hand side, right? So with values smaller than pi over 2, the values of the tangent go up. All right, so we know that the tangent looks like this from 0 to pi over 2. If I reflect that over the x and then over the y, it's going to go like this from 0 to pi over 2, and then like that from 0 to negative pi over 2. So it's going to go down to minus infinity as you approach minus pi over 2 from the right side. Right, and so this is just some values just to kind of show you that it actually happens and not just believe me. The closer I get to pi over 2, the larger these values get. All right, and so you do get the graph that looks like that. That's just between negative pi over 2 and pi over 2. If you want to continue that, well, you have to analyze this function to the right of pi over 2. So you'd have to look at the interval from pi over 2 to 3 pi over 2 separately, and then also from minus pi over 2 to minus 3 pi over 2 as well. And so I have you doing that down below, right? So in the your turns, I have you kind of doing this sort of thing. So I want you to think about the process exactly the same that we just did, right? You want to find the x-intercept each time and analyze using the unit circle what happens as you approach the asymptote from the left and the other asymptote from the right and see what happens. But suffice it to say, once you've done that, what you're going to get is a graph that basically it replicates what happened on minus pi over 2 to pi over 2. And that occurs both to the left and to the right. All right, so check me out on that. But what this suggests is that the tangent function is periodic again, but the period is pi, right? What is the length of the interval that captures one chunk of the entire graph? The length of that interval would be pi. That's how long the interval from minus pi over 2 to pi over 2 is. All right, and so here are your facts about tangent. This is the graph. Tangent is odd, and it's periodic with period pi. So if you take any angle in the domain of tangent and add pi to it, or 3 pi, or 4 pi, or 10 pi, you'll get the original tangent back. Okay, so now what's the inverse tangent? Well, remember, it suffers the same struggle as did sine and cosine in the sense that it's periodic. And so if it's periodic, it doesn't have an inverse on its entire domain. That's fine. We're going to restrict ourselves to a single part of the domain on which it's 1 to 1. And the natural interval to do that for is minus pi over 2 to pi over 2 open, right? So that open interval here generates an entire portion of the tangent graph, right? So it looks like that. And so that's 1 to 1, that has an inverse. And so how do we get the inverse? We draw the y equals x line on this graph as well, and we change the x and the y. But if you do that to a graph that has vertical asymptotes, those vertical asymptotes become horizontal asymptotes for the inverse function because I switched the x and the y. And so for the definition of a vertical line, the equation for it is x equal to pi over 2 and x equals negative pi over 2. So the asymptotes for the inverse function will be y equals pi over 2 and y equals negative pi over 2. Those are horizontal lines. And so the graph you get is this guy here. Okay? We denote that by tan inverse or by arctan, in the same sort of idea. And, oh, hold on 1 second, let me let the dog out again. Okay, so you think about it the same way we did before, right? So for example, what's the tan inverse of 1? Right, so what that question means is the tangent of what angle in the interval from minus pi over 2 to pi over 2 is 1. Right, so these are a little bit trickier because you have to think about how the sine and the cosine relate to each other at these values. So here, the only way the tangent is 1 is if, remember, tangent of x is sine of x over cosine of x. And so the only way the tangent of x is 1 is if the sine and cosine are the same value. Well, we know that a point on the circle for which the x and y are the same occurs at pi over 4. And so, in fact, that's the only one because the tangent's 1 to 1. And so the tan inverse of 1 is pi over 4. All right, and then we have the standard sort of properties here like we did before, namely that the tangent of tan inverse undo each other. Nice thing here about this direction is that the domain of tan inverse is all reals. Oh, no, it's not. Pardon me. That's not true. Oh, no, that is true. Sorry about that. Brain fart. Right, so this one's true. So you don't have to worry about restrictions on this guy. But you do have to worry about restrictions here. Remember, the tangent here, the x has to come from minus pi over 2 to pi over 2. And so if it's other than that, then you have to take the tangent first and then take the tan inverse of that. All right, so let's take a look. Well, why don't you try these? So try to compute these tan inverse values, if they exist or if they don't, and see what happens, and then we'll actually talk about these. All right, so let's take a look at these guys. Arctan of negative 1. So what we want here is the angle for which the sine and the cosine are the same but opposite signs. And so we're looking at pi over 4. There they have the same sign, but at negative pi over 4, the sine is negative and the cosine is positive. But they both are the same distance from the x-axis. And so the arctan of negative 1 is just negative pi over 4. All right, this one is trickier. So if you look at the tan inverse of root 3, we want the angle whose tangent is radical 3. But now we have to try to relate these to memorized values between minus pi over 2 and pi over 2, right? And we know that since the output's positive, the angle that we're looking at is in the first quadrant, right? Because the sine and cosine have to have the same value or the same sign to make sure that the quotient's positive. And we're only looking at minus pi over 2 to pi over 2, right? So I know it's in the first quadrant. So now, if you think back to our values and the definition of sine, we want to find theta for which the sine over the cosine of that theta is root 3. Notice though, I can rewrite this. I can multiply the top and the bottom by a half to rewrite radical 3 in this way. Now you'll say, well, why on earth would you ever do that? Well, the reason is I know an angle whose sine is radical 3 over 2 and whose cosine is 1/2, right? That angle is pi over 3. So I did this so that I would actually recognize what that angle is. Right, so it turns out that since that's true, the tan inverse of root 3 is in fact pi over 3. Excuse me. And then finally here, arctangent of pi, you can't just kill those, right? Arctan and tangent just don't kill each other. You have to make sure that this angle is in between minus pi over 2 and pi over 2 to apply that property. And so what you have to first do is compute tangent of pi. Tangent of pi is 0 because sine of pi is 0. And arctangent of 0, what angle gives you a tangent of 0? Well, that will be when the sine is 0, that's 0. That's how you compute that. All right, go ahead and try these too. So these relate tangent, so sine, cosine, and tangent, and their inverses to each other. They're just composed one after the other. So you just do one at a time and see how it goes. Okay, just additional practice. All right, so let's take a look at them. Pardon me. All right, so for the first one, sine of tan inverse of -1. The tan inverse of -1 we already saw to be negative pi over 4. And then sine of negative pi over 4, you're going clockwise by pi over 4 so that you're down in the fourth quadrant. The value of sine of a multiple of pi over 4 in the fourth quadrant is negative root 2 over 2. And so that's how we're getting that angle. For this guy, the arc cosine of -1/2, right? So what angle between 0 and pi, remember, gives you a cosine of -1/2? Well, we know it has to be in quadrant 2, and that angle is a multiple of pi over 3, so it has to be 2 pi over 3. And then we have to compute tangent of 2 pi over 3. Well, we know tangent is sine over cosine. The sine of 2 pi over 3 is root 3 over 2. Its cosine is -1/2, and so I get negative root 3. And then you do the same exact thing for these, right? So I won't go on with that. It's the same sort of computation, just do the inner one and then compute the outer guy. All right, there are no homework assignments for this one, right? This is just kind of to get you familiar what the tangent and inverse tangent look like. So make sure you go through your turns, just kind of make sure that you have it cemented in, and then I'll go on to the next video. Okay, bye.